Good morning, friends. It gives me immense pleasure to be here again for my course Engineering Thermodynamics. I am Dr. Dwivedi, Professor from Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad, India. As of now, I am running for the next module, that is module number 2, and that is the second law of thermodynamics. Before that, we have seen the first law of thermodynamics, which states that the heat can be converted to the work and work can be converted to the heat. It doesn't say about the direction of the flow of energy. However, the second law of thermodynamics states that the work or heat 100% cannot be converted. There will be some losses. In this process, we have seen the two statements, that is Kelvin-Planck statement, which describe about the heat engine, and another one is the Clausius statement, which explains about the heat pump and the refrigeration. Followed by this, we have seen that how to find the absolute scale of the temperature, that is QL by QH is equal to TL by TH for the reversible cycle. We have seen the Carnot cycle, we have discussed, we have derived the efficiency of Carnot cycle. We have seen that how the Carnot cycles consist of 4 cycles. First one is reversible adiabatic compression. Second one is reversible isothermal heat addition. Third one is reversible adiabatic expansion. Fourth one is reversible isothermal heat rejection. We have also derived the efficiency of the Carnot cycle, that is the eta is equal to 1 minus QL by QH. And this Carnot theorem says that the maximum efficiency which we can achieve is what he has given the cycle, that is the Carnot cycle. For any reversible cycle, this is the highest efficiency. So if in a given temperature, the temperature will give how much efficiency you can get it. After that, we have seen the Clausius inequality. In Clausius inequality, we have seen that how the cyclic integration of del Q by T is 0 for the reversible cycle, and the cycle integration of del Q by T is less than 0 or minus or negative for the irreversible cycle, and del Q by T is greater than 0 is not possible. Positive is not possible. We have also seen derived the entropy. First time the entropy, we have derived that del Q by integration del Q by T is equal to ds, and this ds is a change of entropy. And we have also discussed something about entropy in our just previous lecture, and now today we are going to discuss about further explanation and the derivation of the entropy equations, principles of entropy increase, Gibbs equations, third law of thermodynamics, entropy of a solid, liquid and the perfect gas derivations. So this we will be learning in today's class. Hope in last class we have seen the Clausius inequality. So it is cyclic integration of del Q by T 0, then 0 and 0. This is the reversible cycle, this is the irreversible cycle, and this is not possible. This we have already discussed in our previous class. Other form, I have shown the two different forms of this Clausius inequalities. Then we have find out that dq by dt is equal to ds, or this d, or cyclic integration of del q is equal to tds. So this is the, we have find out, and where this ds is a change in entropy. This we have done in, and we have seen the TS diagram for the, if you see here, TS diagram, TS, so 1 to 2, that is the adiabatic compression, 2 to 3 isothermal heat addition, 3 to 4 is adiabatic expansion. This is the compression, and this is the heat rejection. This is the isothermal heat rejection. All are reversible. Okay, so this is the TS diagram, and from the TS diagram we can find out the work done. This is the, it gives the Q. Q is equal to T into ds. So the area of this will give how much heat is needed, and this will give the work done from the first law of thermodynamics. So this we have seen. Now we will find out some new equations for this entropy derivation, some how to derive. I think this I have covered in my previous class also, but just it is a revision. So from Clausius inequality, we have find out that cyclic integration of del q by t is equal to 0 for reversible cycle only. Here if you see the process 1, 2 and 1a and 2, another it is going from 2b and 1. The another process is going 1a to 2 and from 2c to 1. Two process, both are the reversible process. So by the Clausius inequality, we will see here that cyclic integration of del q by t is equal to 0. This indicates that 1 to 2, the integration of 1 to 2 via a, so here 1 to 2 del qa plus divided by ta plus 2 to 1 del qb by tb is equal to 0. Taking another path, that is 1, this is 1a to c and 1. So del q by t is equal to 0. So here 1 to 2 del qa by ta plus 2 to 1 del ql by tc is equal to 0. Now subtracting from 1 to 2, we will get here 2 to 1 del qb by tb is equal to 2 to 1 del qc by tc. So here this you can see the cyclic integration of del qb by tb, del qc by tc. If you have some more cycles like d, like here, like the return from here to here, here to here in this cycle, it may be e. So here you can see that cyclic integration of del q b by tb is equal to 2 to 1. Cyclic integration of del qc by tc is equal to 2 to 1. Del qd by td is equal to 2 to 1, and so on. So whatever process you take, for all the processes, the ratio of change in heat and the temperature of that thing will remain constant. From there we have derived the equation, and this property, that is 1 to 2 are initial to final. Del q of reversible cycle by t will be same for all reversible paths. Any reversible path, the ratio of del q by t will remain same. So here del Q reversible by T is equal to ds. This ds is a entropy. This is entropy change or change in entropy. So here we got del S is equal to del Q by T for reversible. This is the entropy change ds, and this is the one special property of a system. So this we have already in the last class also I have discussed, but further I have explained here this thing. Now if we take the process, we have seen in the previous one that this is only for the reversible cycle, but since this point 1 and the point 2, they are the property point, they are not dependent upon the path, they are independent of the path. So whatever path you go, maybe the reversible or the irreversible, the point 1 and 2 will remain the same. So that we have seen here that in a PV diagram, this it is starting from 1 here, it is going by 1A2, another is 1B, it is jumping like this, it is an irreversible process, and this is a reversible process. It is every point in the paths are also known in this, but here we don't know how it is, but we don't require also, because within the 2 points the entropy will remain same. So here we have shown here that this dotted line is your irreversible line, and we do not know the point in this. So del Q is a path function, we know that. So we know that delta S reversible from the A is equal to delta Q reversible by T. Here S is a function for a property. We cannot get path on the irreversible process. So if you see the path B, so this delta S is equal to delta S reversible A as calculated for A. So if you know this 1 and 2 by the reversible process, if any process are going irreversible also, the S1 and S2 will be same. So here delta SB is not equal to delta QB by T. This SB is not equal to delta QB by T, but it is equal to delta S reversible. So this is the statement, the Clausius statement, that delta Q by T is not equal to 0, not correct. So we can see that how other these like units of specific entropy, this we can see the other units of this thing, but delta S is not equal to delta QB by T, but it is equal to delta S this reversible cycle, delta Q reversible by T, but not delta QB by T, as Q by T is less than or equal to 0. So here we can see that now the third law of thermodynamics. So here first we will see the S is a entropy, it is a joule per Kelvin. When we say small s, it is a specific entropy, that is del Q by T, it is a small q T, or here del Q by T into MT, or joule per kg Kelvin. So this is specific entropy. Now we will discuss about the third law of thermodynamics. And so various statements are there, but one statement which I am here depicting is for the pure substances, if we reach to the absolute temperature, the entropy is 0. So here it says that before that we have seen that only delta S. Delta S means it is a change of entropy. But third law says that at absolute temperature, when we reach at absolute zero temperature, the entropy of the system for a pure substance or pure crystal will be zero, which gives some reference to entropy calculations. We know that del Q by T is a difference at T is equal to 0, there is absolute 0. In that, delta S will be 0. This is from the third law. We know that from the first law that dE is equal to del Q minus del W, or del Q is equal to dE plus del W for simple compressible substances. We can make this dE as E means U plus kinetic energy plus potential energy. For the simple compressible substances, these two things are 0 and 0. So E will be U. So we can write here that del Q is equal to du plus del W. But for the del Q, we can write the TdS as per the definition. So here we will write del Q is equal to TdS, which we have already find out, is equal to du plus PdV. So here what is the PdV? PdV is a work done for a simple compressible substances. Here we are not taking other work, only the thermodynamic work PdV, when it is changing the pressure and the volume of the system. Here this type of work as shown here, this is the gas here. If it is going like this, or it is going like this, if it is going down, it is minus W and this is the plus W. So work is done by the PdV. So if we divide here by M, so we will get here ds by M, U by M, V by M. So we all will get here a specific entropy. So here T into D small s plus D into small u plus P into specific volume. This is called the Gibbs relation. This is called Gibbs relation. So TdS is equal to du plus PdV. This we have got one very good relation on that. So as a statement for the third law of thermodynamics, the third law of thermodynamics states that the entropy of a system approaches a constant value as the temperature approaches absolute zero. The entropy of a system approaches a constant value as the temperature approaches absolute zero. The entropy of a system at absolute zero is typically zero, and in all cases is determined only by the number of different ground state it has. So only one condition, when absolute temperature is 0 Kelvin, that time it will be a constant value of entropy, and this will be 0, and that is the datum point of entropy, and from here you can start. In other cases, this will be the different S, that is the delta S. It is a difference between 2 points, but at K temperature is 0 K, S will be 0. So this is the third law of thermodynamics. It states about the entropy. It defines the entropy. So the third law of thermodynamics states that the entropy of a system approaches a constant value as the temperature approaches absolute zero. and the entropy of a system at absolute zero is typically zero, and in all cases is determined only by the number of different ground states it has. So this is the third law of thermodynamics. Now we will discuss about Gibbs law and how this Gibbs law is working, and we will get some relations and the derivation of the equations. So we know that H is equal to U plus PV. So dH is equal to du plus pdv plus vdp. So this du plus pdv, du plus pdv, we can write dh minus vdp. So here we will get tds is equal to dh minus vdp. This is called the Gibbs relation to find the changes in entropy. So previously we got one relation that tds is equal to du plus pdv. This is the pdv, and tds is equal to ds minus vdp. These equations for all processes, not only for reversible, this can be used for any type of processes which are used for the systems. Property relations depends on the initials and the final states, can be used for irreversible processes also. So in this process, if you see it is a TS diagram or whatever is there. So this is the reversible and this is the irreversible. So once you find this 1 and 2, then this 1 and 2 will be applicable for irreversible process also, and this was derived by the Gibbs. So this is called the Gibbs equations also, and the Gibbs relations. So here we have TDS is equal to du plus PdV. Another relation we have TDS is equal to du minus VdP. DH, it is not, this is the U and this is the H. Okay, so DH minus VdP. So we will see that first we will see the two examples. One is for the solid and the liquid, the example 1. So first we will see that TDS is equal to du plus PdV. So for the incompressible, it is called incompressible. It is for the incompressible substances like liquid and the solids. We have to use this equation that TDS is equal to du plus PdV. The change in V is very small, so dV is equal to 0 here. So here dV is equal to 0. So here we can see that TDS is equal to dV because this has become 0 because as per this here. So this du is equal to CV dt. So this ds is equal to CV dt by t. Now you integrate this. Integration of ds is equal to CV is constant 1 to 2 dt by t. So if you integrate, you will get here delta S is equal to CV ln T2 by T1. So this we have got here that delta S is equal to CV ln T2 by T1. This we have got one equation by the help of the Gibbs equation, that how to find out the entropy change. This is change in entropy. So CV ln T2 by T1 is equal to delta S. We have achieved by the help of this equation. Now we will see for the next about for the gases, and for the gases we have the one is ideal gas, another is a perfect gas, and what is the difference between the ideal gas and the perfect gas, that we will be discussing. That especially the specific heats for the perfect gas will be always constant, but for the ideal gas, it is depend upon the temperature. So this Cv is a function of the temperature, but for the ideal gas or calorifically perfect gas, that is called the perfect gas, C will be constant. Okay. Now, derivation of entropy for an ideal gas. So this we will see here that when change in phase, latent heat temperature to be used for T. So if it is TS diagram and it is like this, if it is change in phase from here to here, you use this temperature. If it is here, then you use, but if it is, it will remain constant inside this dome. So for the, if you are using this equation for the change in phase like water to vapor or nitrogen or some refrigerant they are used, then use this latent heat temperature. So this point you have to take care of. So change in entropy for the ideal gas, we know that TdS is equal to du plus PdV. So we can write here that du is equal to Cv dt plus PdV. So ds is equal to Cv dt by T plus here PdV. So for the PdV, we can write PV is equal to RT, or P by T, we can write R by V. This P by T by the PV is equal to RT. So P by T, we can write R by V. So here this we have taken here that ds is equal to Cv dt by T plus here R, this dV by, this is the dV. So dV by V. Now we have to integrate from 1 and 2. So this delta S is equal to Cv 1 to 2 dt by T plus R 1 to 2 dV by V. So this Cv is equal to log or ln T2 by T1 plus log V2 by V1. So here we got this, that change in entropy S2 minus S1 for the ideal gas is equal to Cv ln T2 by T1 plus R ln V2 by V1. So entropy change by the Gibbs equation. This is another equations by the Gibbs. We have further derived the entropy change for the ideal gas with the help of the Gibbs equation. Okay, here we can see the further from the help of the pressure and the enthalpy. Here H is enthalpy. So we have seen that TdS is equal to, another equation is dH minus VdP. So here ds is equal to, dH is equal to Cp dt by T minus V dP by P. So here Cp dt by T minus V by T, we can by PV is equal to RT, PV is equal to RT. So here for the V by T, we have taken this V by T is equal to R by P. So for the here V by T, we can write R by P. So here Cp dt by T minus R dP by P. If we integrate this, we will get del S is equal to Cp 1 to 2 dt by T minus 1 to 2 R dP by P. So if we integrate here, we will get S2 minus S1 is equal to Cp naught. What is the Cp naught? Cp naught is for the perfect gas. This is for the perfect gas, where Cp naught will be constant, and this is not function of the temperature. This is not the function of temperature. So here S2 minus S1 is equal to Cp naught ln T2 by T1 minus R ln P2 by P1. So for the perfect gas, this is the equation, and for the ideal gas Cp will be there, and this is the function of temperature. So that is the difference between the ideal gas and the perfect gas. So for the perfect gas, S2 minus S1 is equal to Cp naught, where Cp naught will remain constant. It is not the function of temperature. If it is the function of the temperature, then the integration here, Cp dt by T will be taken for ideal gas, as Cp is a function of temperature. So that much we have to take care, that if it is mentioned that it is a perfect gas, you use the value of Cp directly, but if it is ideal gas or any other gas, Cp has to be taken as per the temperature, not as per the constant value. Now I will discuss about PV and the TS diagram, and we have to find out the work and the heat of the system. So here, this is the piston here. This is the piston and this is the cylinder. Here is your gas is filled here. Now, if you expand from 1 to 2, this is the position 1, and if you make it here, again it has reached from there to here like this. So this is the 1 and 2, it is expanded from here to here. So in PV diagram, this is the point 1, and this is the process, you will reach to the point 2. So here del W is equal to P into dV. So what is the dV here? This is the dV. So dV you have got here, and what is the P? P is the average pressure. So P1 and P2. So average pressure P is equal to P1 plus P2 by 2. So this pressure you have to take in this, and this dV is equal to difference of V2 minus V1. So this dV is equal to V2 minus V1. So now this del S is equal to ds is equal to del Q reversible by T, or d small s, that is specific entropy, is equal to del small q by T. So here TS diagram, in this TS diagram, area under this curve will give the heat transfer. So this del Q is equal to T into ds. This is the area which is under this curve, will give this del Q, and area under PV diagram and work will be P into dV. So area under PV diagram will give the work, and area under TS diagram will give the heat. This is called heat transfer. We will get heat transfer. And so these plots gives the visualization of heat and the work. So PV diagram gives the how the work is in process, and the TS diagram will give how much heat is absorbed and how much heat is rejected As per the, if it is expanding, means heat is rejecting, and if it is contracting, heat is removed from the system. So that we have to observe and that we have to see it. So in the next class, I am going to discuss about principles of entropy increase, entropy generation, statement of increase in entropy principle, availability and irreversibility, decrease in availability when heat is transferred. These are the references so this I will be discussing principles of entropy increase in my next class, entropy generation also in the next class, statement of increase in entropy principle, availability and the irreversibility, decrease in availability when heat is transferred. These are the references which I am referring. The P.K. Nog, Engineering Thermodynamics, McGraw-Hill's, Eunice Sengel, very good book. Michael A. Bowles, Thermodynamics and Engineering Approach. Tata McGraw-Hill's, 7th edition. Then this is the NPTEL lecture from Dr. Mishra, IIT Kanpur, Engineering Thermodynamics. It is very good lecture, and also the Dr. Sumant from IIT Kharagpur, very good lectures. You can see them. Any questions, you are always welcome to ask. Please like and subscribe this channel. I will be very grateful. Any questions, you are welcome to ask in my email @gmail.com. I will be very happy if you are sharing any queries or anything which you feel is not appropriate or it is not correct. You are always welcome to ask. I will also like to thank you for listening me and hope you will see my next lectures also in the same way which you are seeing me again and again. Thank you very much for the joining, and we will meet you for the next lecture. Till then, goodbye.
Like, share and subscribe. Hit the bell icon for more updates.